Hello everyone, I'm Qinghui Wei from Fudan University, and it's my honor here to talk about our work, Deep Hybrid Self-Prior for False 3D Mesh Generation. In this work, we present a deep learning pipeline that leverages network self-prior to recover a false 3D model from the colored 3D point cloud. The 3D scanners are effective tools for high-res 3D model collection. Unfortunately, most 3D scanners only produce colored point clouds as the output. Given such a situation, we propose a robust method for reconstructing a false 3D model from the colored point cloud. The Poisson surface reconstruction is an indicator function and uses its gradient field to solve the Poisson equation. However, this approach requires accurate normal orientation, relies on dense point cloud, and struggles to handle non-tight cases. Deep learning provides new opportunities for geometry reconstruction. However, most methods rely on data prior learned from dataset and suffer from generalization on training sets. Recently, Point2Mesh proposes to exploit self-3D prior from network, which deforms an initial mesh via fitting mesh CN on the input data. However, the 3D price of the network from unstructured 3D data is not strong enough, and the performance is highly relative to the quality of the input point cloud. Meanwhile, the deep image prior has shown its strong ability for self-supervised 2D image reconstruction tasks, which uses the 2D network as a prior without need of any additional training data. Inspired by the success of deep image prior, we propose to use the network structure as a prior, which exploits the hybrid 2D 3D self-prior to enhance the smoothness and robustness. We design a hybrid prior network to leverage self-prior in both 3D and 2D space, and an overview of our system is shown as this. We first run a 3D self-prior network for initialization, then improve the geometry quality and produce texture map in UV space, which generates dense XYZ map and RGB maps. The dense maps are unprocessed to update the vertex location in the 3D mesh, which is then fed into the 3D network for iterative refinement. Now we introduce the 3D self-prior network and 2D self-prior network in detail. Similar to Point2Mesh, a convex tail is generated for its initialization and deformed iteratively under the supervision of the point cloud via mesh CN. The loss function is redesigned for computational effective and faster convergence. We then refine the mesh via a 2D prior network. We first create a UV atlas from initial mesh, then we project the point cloud to UV space to get sparse maps. Then the 2D prior networks are trained to produce dense maps supervised by sparse maps. Then we update 3D vertex locations with predicted dense XYZ map. To fix the artifacts introduced by the 2D prior network, we send the updated mesh back to the 3D prior network for another refinement. The two networks run iteratively to improve surface quality gradually. We compare our method with SOTAS on data from various sources, including synthetic data collected from the internet, data from Point2Mesh, and the real scans from 3D scanner. This slide shows the quantitative comparison with SOTAS on synthetic data. We make further comparison with Point2Mesh on various datasets following their setting. This slide shows the qualitative comparison on synthetic data. Our method shows consistently better performance. We can see that Poisson reconstruction generates incorrected meshes for thin structures. The results of Point2Mesh are relatively noisy. We also test on scans collected from the split scanner. Compared to other methods, we produce overall better geometry for smooth surface, sharp boundary, thin structure, and sparse areas. We tested the robustness of method by manually adding Gaussian noise on input point cloud, and the results are shown in the slide. We also show quantitative results on the right. We also test the robustness of our method on sparse input point clouds. We run Poisson, Point2Mesh, and our method by taking input point clouds with different number of points. As expected, the performance of all the methods drops when the input point cloud number is decreasing, but our performance drops slower than the others. More details about this work can be found in our paper, and the code is also available on the project web page. That's all. Thank you.